I'll begin with a word of prayer. So, dearly Father, we thank you for this day. Again, I thank you for these students, both of them. Help us to learn what we need to and just to glorify you in what we do, Lord. In your name I pray. Amen. So, yes, this is the second course in analysis, although some people would say it's not. It's like, I don't know what it is. But I'm not sure how well this is going to fit in with either of your real analysis. I think both of you have a real analysis background, which is pretty similar. And I think you both use Bartle, and you probably both got to more or less the same place. And I probably should think about that more as the totality of the course unfolds to make sure like I'm not missing something for you guys. But because I haven't had enough time to do these kinds of soul searchings, I'm going to be very boring and just start at the start of the book. So the book is Introduction to Hilbert Spaces with Applications by Debnath, and Piotr Makunsky. I am sure I'm mispronouncing those, but this book right here. And this book was actually the textbook for, I think, my graduate analysis class, but we never really used it. And it says in the start it's for like upper level undergraduates or starting graduates, which is kind of like the level that we're aiming for in this class, right? So just to give you like a sort of a bird's eye view of what we're going to do in this course, we will start by talking about normed vector spaces. All right, so like that's mostly what we're talking about today, is what's a normed vector space. Some examples of that, especially interesting examples, will include like function spaces. And then along the way we'll give a precise meaning to the term Banach space. And sort of the conclusion of chapter 1 concerns the contraction mappings and the Banach fixed point theorem. That's a very interesting result, and hopefully I will actually show you the proof of like the existence and uniqueness theorem for something. Not sure what, but I should do some kind of like deep existence theorem in here, because that's what that allows us to do. I think it's probably not an exaggeration to say most of the interesting existence and uniqueness theorems in analysis in one way or another are due to the contraction mapping idea. Now then, chapter 2 is on the Lebesgue integral, or Lebesgue. But so yeah, the Lebesgue integral. And I'm less well versed in that, but we'll get through it together. I've taught it once before out of a different book, but I think this book is pretty accessible, and like I think we're going to enjoy it. Basically, the Lebesgue integral is a way of formalizing integration which extends past that like basic Riemann integral you saw in calculus, and it gives us a context to do integration theory more carefully. So there are any number of really simple claims in ordinary integral calculus that if you really tried to prove them from the definition of the Riemann integral, it's really, really difficult. Like for example, if you try to prove directly from the definition of the Riemann integral that the integral from like A to B and then B to C, so like this, let me just write, it's easier to write it than to say it. So like this relation. This is a really weird first thing to write in this course, like really weird. But it's just, I'm having trouble verbalizing it, so here we go. So this thing, like we don't ever prove that in calculus 1. What do? Yeah, we draw a picture, right? We go, okay, so if you look at the signed area from A to B, and you pick a point in the middle, it's the sum of the areas to the left or to the right of the middle one, right? And that's kind of it. What if you actually tried to prove that directly from the definition of the Riemann integral? See, the natural proof there, you'd have to take the partition that's built from like A to B and like split it into two partitions, right? One that goes from like A to C and the other one that goes from C to B, and then sort of like do some sort of reindexing and you can prove it that way. It's in my calculus notes. It took me a long time actually to come up with that argument. It's weirdly technical. I think that that result becomes like one line in this other way of thinking. It becomes really, really natural to prove things like that. So that's, part of the larger subject of measure theory, right? And this is not the most abstract, highbrow version of measure theory in this book, right? There's you can make measure theory more complicated than this book does, I think. All right. So, but I think it's a good first exposure to the idea. And it even talks about the Lebesgue integral and the Riemann integral. That's section 2.10 in this book. Yeah. The other thing that might be an adjustment is there is some amount of complex things scattered throughout this book. So we do some things over the complex numbers, do other things over the real numbers, starting with what we'll cover today. And then chapter 3, so let me just say it in words. A Banach space is a normed linear space which is complete. So it's a complete normed linear space. This is what a Banach space is. Complete means that every Cauchy sequence converges to a point within the space, which we'll talk about. Then in chapter 3, we start looking at what are called inner product spaces, right? And then if you have an inner product space, which is a complete inner product space, well, that's what's called a Hilbert space. So a Hilbert space is a space which has sort of an abstract dot product. And if you set up notions of analysis with respect to that abstract dot product, it behaves very much like the real numbers, is one way to look at it. So Hilbert spaces are very nice. They have nice properties, and that's what chapter 3 and 4 are about, I suppose. Well, chapter 4 is about linear operators on Hilbert spaces, so hopefully we'll cover that. Then chapter 5 is applications to integral and differential equations. So I might actually get a little bit out of order and do part of that right at the end of chapter 1, because I don't want to wait. Like, I want to do the existence theorem, I might want to do the existence theorem earlier rather than later before I get too tired. So anyway, there is, okay, so in differential equations, I think the first course we see in differential equations is largely concerned with what? Like precise solution, like algebraic solutions, closed form solutions to the problem, right? And then of course, towards the end of the course or somewhere in there, we start looking at series solutions, which I would still say are precise solutions, right? But precise is I'm using precise in an imprecise way, and I'm aware of that. But sorry, I am a dad. At some point, you want more, and so like the more sort of grown-up way of looking at differential equations is more like something like, I don't quite entirely understand this way of thinking about things, so I can't really do it justice, but they start looking at weak solutions, and the problem starts to become more about estimating how much of a solution it really is a solution or something like this, or I don't know. Hopefully we'll get into some of that more sort of grown up, if you will, way of thinking about differential equations. Maybe not actually. Yeah, my bad. I think what I'm talking about vaguely right now would be weak solutions of elliptic boundary value problems. That's actually in chapter 6, 6.5. That's something I need to learn more about personally. But let's see here. So chapter 5 is chapter 5 just seems to be about existence and uniqueness of differential equations in the sense that you'd see in the first course. So basically chapter 5 is about giving proof for things that we just do in differential equations, which is good for a math major to see, right? And that's also why differential equations used to be a higher level course in math departments, because some of that existence and uniqueness stuff used to be in the regular course. But no one in their right mind would prove an existence theorem in differential equations right now. That said, I was able to take the existence and uniqueness proof in the appendix for Nagel, Saff, and Snyder, and that actually was sufficiently technical that I was able to like adapt it for my research purposes. So like, I don't know, it's good that some of the books that are around still have some things which aren't taught. It's a shame when our textbooks just become what's taught and not what we know. I digress. And then chapter 7, that's the real reason I picked this book for both of you have some interest in quantum mechanics and physics. That's not everybody. Like, you are a smaller subset of the universe of mathematical graduate school bound math students. And so I'm glad that both of you are interested, because I'm interested too in like trying to teach this chapter 7. And I've read it before, and I found it to be really, really nice, because physicists kind of just teach by notation a lot of times. And this puts frameworks in place to explain the difference between like the Schrodinger and the Heisenberg picture and things like that. And then chapter 8 is on wavelets and wavelet transforms. I don't intend to cover that. And I don't intend to cover chapter 9, except I see that it has the Guitau, I'm mispronouncing that, and Fouché differentials. And I might say something about that if there's time. I don't know. So that's basically my intention, is to try to cover everything in here as much as I can. And so I'm just going to just dive in and just start working through the book, yeah? In terms of homework, so like a lot of your grade is from homework. I know you guys, you just want to learn, you don't care about your grade. So that's cool. But where was it? So I had to make a syllabus up, you know? And so like my syllabus is very silly. It's just like, you know, norm vector spaces. What is it?
Oh, I was going to say something.
Oh, if you have it?
Sorry, my bad. Thank you. You're going to start the end.
No, you're fine. I'm trying to remember what I put down in the syllabus in terms of points. I mean, somewhere I put, oh, here it is. So I put test 1, 100. That's not right. Test 1, 100 points. Test 2, well, maybe it is. I guess, yeah, I put test 1, 100 points. Test 2, 100 points. Homework, 600 points. And final exam. So, like, mostly you guys need to work homework, right? And then once we get to a place of understanding, we'll have a test, yeah? I'm not sure when that'll be. I might have said so in the syllabus, but... Oh, yeah, I said that test 1 was February 13th. I wanted it to cover up through the Lebesgue integral, and then test 2 was going to be March 24th, and I was hoping it would cover pretty much almost to quantum mechanics, but I don't know. This is not written in stone. If we need to change it, we will, right? I just had to put something down so we could get started. And but okay, so like for the first homework assignment, which you cannot do, Audric, you know, without the book, unfortunately. Maybe, you know what I can do? I will scan it for you.
Yeah, I went to Amazon. It's just like technically still pending. I like just put 2-day shipping on it and see if it is any. But you know, Livingston, who knows what 2-day shipping means?
Yes, I hear you. But I'll just get my phone out and I'll scan the problems at the end of the chapter for you. It won't take me too long. It's only a couple pages. Then you'll be able to look at that. And so maybe if I pay Daniel $2, he'll scan the chapter for you. I don't know. Quasi-legal PDFs of this do not exist.
I heard nothing.
You heard nothing. Good answer. Okay, so all right, so the first thing to settle is normed vector spaces. So let's just get straight into that. I won't write everything down because I think you guys already know some things. So let's see here. So first of all, do we know what a vector space is? Okay, so we know what a vector space is. Good. So vector space, let me just say it in words. Vector space over, let's say, K. What does he use K? Oh, he uses F. Is a set. He uses E for that, paired with addition, right, which is a mapping from E cross E back to E again, and scalar multiplication, which goes from what? From F cross E back into E again, right? So it has addition, it has multiplication by scalars, and what else? You say continuous?
Yeah, the properties.
Oh yes, it has property. What are the properties like? So what can we say about the vector addition?
Linear.
It has linearity. I mean, yeah, I think that's kind of it. So this guy is what? It's commutative. There's a 0, right?
Are we saying it's a ring?
There is. Yeah. Well, let's see here. If I do this, minus x plus x equals to 0, x plus y plus z, x plus y plus z. So if you look at the three things I just wrote, right? What is this? These three things here. This says that if we just look at the vector space E with respect to its addition, it's a group with respect to addition, right? So it's a group under addition, where 0 is the identity, and we do, the inverse is negation. Then the top thing says not just a group, right? It's an abelian group with respect to addition. I mean, pretty much, if you write addition, you're assuming it's an abelian group. That's the common practice, right? If you find somebody who's writing a textbook where they're using the plus symbol for a non-commutative thing, that's probably Dr. Sprano. But that's the kind of thing he does. To get the students, but it is a convention to write plus for abelian groups. And then the scalar multiplication is that linearity you're talking about, Audric, right? Like the constant times x plus y is the constant times x plus the constant times y. And of course we start dropping the dot and just using juxtaposition for the multiplication. And then it also works with the constants, right? Like this. So you've got both of these notions of distributivity. They're not exactly distributivity, right? Because, they're scalar multiplication. What they are is they define scalar multiplication. Of course, the other thing that's important at some point or another is that 1 times x is equal to x again, right? So like the scalar multiplication of the number 1 in your field has to be just that. All right, what else? So when f equals to r, it's a real vector space. What else? If we have f equals to c, it's a complex vector space, right? What else can I say? So some examples. Number 1, Rn. Number 2, Cn. Number 3, oh, you're fine. What is it? Is it something?
Infinitely differential, I think. Yeah.
Oh, yeah. I don't know where I am. I'm going my own way. Infinitely differential. Yeah. Okay. So let me just. I'm going to take a slightly more abstract viewpoint than the book here for a second, but you're all good. So, and you guys know what Rn and Cn mean, right? It's fine. Okay. So, if we have S as a set, yeah. Then V vector space, you can define E to be F from S to V, F a function. And this will define a vector space. So Yeah, okay, so he does that. That's his example 3. Yeah, cool. He used a different letter, but this is the same idea. And the reason that this is a vector space is you just need addition. Like, what's the vector addition? It's the, how do you add functions? What?
Taylor said, like, just how we usually do it.
Just how we usually do it? Yeah, you're right. So if we have f plus g, how do we define that? Well, we define that by f plus g of s is f of s plus g of s, right, for all s and s. And that is a rule which defines a new function, f plus g, from the functions f and g, right? So, and likewise, how do you scalar multiply? Well, you just, like you said, like we usually do, right? So the reason that makes sense is you notice that the addition and the scalar multiplication, they're all happening in the place where the function takes its values, right? So because you're assuming that V is a vector space and that f of s and g of s and are in the vector space. And we should say vector space over what? Like over f, right? So the field matters. So then E will likewise be a vector space over f. So here C is in the field. All right. And this covers a multitude of examples, really. All right. So what's the zero vector? He says the zero vector in f is the function which assigns the zero vector of E to every element of x. So he uses, I said E is, so here's the difference between what he wrote and what I wrote. I said E is the thing we're defining, and he put his E here. I don't think he even gave a name to the thing. You just, if I want an abstract name for this, I'll say E is like functions from, S to V. So sometimes I'll use that notation.
Wait, he's calling the zero just a constant function?
Yeah, 0 is the constant function. That's right. All right, so moving on here. So example, so he then says, okay, so what's a subspace? So many subspaces of function space are of interest, right? So like, oh, wait a minute, that's fine. Let me zoom back out a little bit. Well, we'll figure this room out eventually. So what are his subspaces? All right, let's get to it. So we need to know this notation, right? So he says, let omega be a subset of Rn, and he says that this is an open subset. Golly, does that? What do I mean by open subset? Is that okay? So I don't know. Your real analysis might have just been in R. Okay, so so what it means for a set to be open in Rn is that at each point in omega is an open is an interior point, which is to say that you can find an epsilon ball around that point with respect to the Euclidean notion of distance. I think he gets to this stuff later. I think he just wants his example now, and he'll get back to defining open later, maybe. Or not, I don't know. Let's see here. So, okay. That's on page 14? Yeah, we're on page 4 right now. That's funny. Yeah, okay. Well, yeah. So technically speaking, we need page 14 to understand what's being said on page 4 here. But it's okay. Let's go on, because we have an intuitive sense of what open means anyway. Okay, so here we go. And he says that the following are subspaces, the following are subspaces of the function space from omega into the complex numbers, right? So complex numbers, and so I would think of these as real vector spaces, I suppose, but I suppose you could go either way. So C omega. I have trouble with the omega today. C omega, C k omega, C infinity omega, and P omega. What are these guys? Yeah, so the first one, this is, yeah, continuous functions. Just continuous functions, right? This is k times differentiable. Now, does he assume, this is important, does he assume that the kth derivative is continuous? Continuous partial derivatives of order k. Ah, yes. Let's say, so we could say, so there's a couple different ways to say this. The way he said it is the most untechnical way, but you could say this, it's k times k differentiably continuous perhaps, but I'll just stick with his statement of it, which is it has k derivatives, not partial derivatives, right? K partial derivatives continuously so. Sorry, my grammar is not great there, but you get the idea. So for example, there are functions that are differentiable one time that would not fit in here, in like C1. There exists functions where the derivative exists, but the derivative itself is not continuous. So like that kind of example is in some sense forbidden by that, at least at the level k. I mean, you could have an example which was continuously differentiable to order 1, but not continuously differentiable to order 2. There's all kinds of wacky stuff that can happen. Have you ever seen that example? You know what I'm talking about? The continuous but not continuously differentiable?
I think we covered it in complex a little bit.
Isn't it the sine wave with the point at like 0?
Yeah, the sine. I usually use that. It's like if I can graph it. You know, something like you basically got this sort of like envelope like this, right? And then the function that we're talking about oscillates between those.
Is it like sine of 1 over x or something?
Yeah, like sine of 1 over x or something like that. You can concoct such a function so that its derivative will exist at 0 because it gets pinched down to existing, right? And yet the derivative is discontinuous at 0. So you can design such a function. It's everywhere differentiable, in fact. But that derivative is not continuous at 0. So anyway, I'm sure that'll come up again later. So that's why this continuous continuity of the partial derivative stops that kind of thing from happening. I mean, this is just a one-dimensional example, but this phenomena persists to like functions on the plane or the volume or anything. I mean, you can do that for 1 dimension. You can do it for 2 or 3. This is just what I would call smooth functions. What's that mean?
They got nice Jacobians.
Yeah, nice Jacobians.
They're infinite, like they're when you like take the partials, you just keep going forever. Right?
Exactly, yeah. This has partial derivatives of arbitrary order, and every order is continuous because if you can differentiate the partial derivatives and get the next order, if they were not continuous, that would be a strange issue because we know that you know, differentiability implies continuity. So like if you can take, okay, and then this is just polynomials. Okay, so then the question is, why are these subspaces of function space? how would you establish that truth? Yeah. I mean, so the short answer is the subspace test, right? So like, you take two elements in here and take your favorite scalar, and you can show that cx plus y is an element of that, again, maybe I should use f, like cf plus g is an element, again, of the same type, right? If I take two continuous functions, right? If I take f and g in here, right? Then cf plus g is again an element of c omega, right? Because the sum of continuous functions and the scalar multiple of a continuous function is again continuous. That's the limit laws, if you like. Now, although I think I'm abusing things a little bit here, we're not talking about functions of a real variable, right? We're talking about functions defined in an open subset of Rn. Do you have a question, Audric?
Scalar not matter?
Oh, well, yes, yeah, the scalar can be whatever, like C is an element of, I think, I'm going to say R. I'm going to think about these as real vector spaces.
Well, I'll just,
Maybe I shouldn't, though.
If you have a subset tight enough, like, can you use the really big scalar? Wouldn't that give you a vector kind of outside that?
Oh, no. If you have a continuous function and you scalar multiply it, you still got a continuous function.
Yeah, but does it come back into omega? That's my question.
It goes back into C of omega.
Yeah, exactly. It comes back into C of omega because it's, again, a continuous function. Like, what does it mean?
Oh, I got you.
Yeah. Now, I don't know. I said just a second ago that these are real vector spaces. You could go either way, though, right? I mean, you could say that these are complex vector spaces, or you could say they're real vector spaces. You could go either way.
You're mapping into C right now, right?
Yeah. That was what the starting point of this was. They were mapping into C. But obviously, we could say that we could replace C with R and still do this, right?
Yeah.
In fact, you can replace C with a vector space and still do this. It's just you wouldn't have complex valued functions anymore. You'd have matrix valued functions or whatever valued functions, right? Like, this construction is not limited to just complex valued functions. That's why I was saying over here, this is an incredibly general example. I don't think we really, it's easy to sort of just glide past how abstract that is. Because S could be any set. You don't need a linear structure on S at all to define those. All right, so next example is one which is sort of the bane of every analysis. I think this was his example 4, by the way. And his example 5. Oh, I gotta be careful. I work over here, right?
Yeah.
Audric is like, you can erase. I think the webcam stops like here, right?
Yeah, right there.
Yeah. So the next example is sequences. All right, sequence spaces. So let me just call it, I don't know, does he have a notation? Okay, he's still working. I mean, see, I'm always like, I'm debating, like, what kind of sequences? Because you can talk about sequences in anything, right? So essentially this, if you, like here, let me be slightly more abstract. You could look at the function space from natural numbers to a vector space, right? This would be sequences inside the, a vector space. So his context is he wants to look at sequences, complex valued sequences, right? So this would be a set of complex sequences. So these are just, you can look at them as lists of complex numbers if you like, right? And how do how do you add and scalar multiply? I mean, I mean, we already defined it, right? Back in example 3, but what does it look like in the sequence notation, right? Right, it's term-wise, because you're just listing the values of the function in this notation, right? I mean, it's not different actually than this example. It's just we use a different notation for it. Like what I'm really saying is, if we have x plus y and we let it operate on the integer n, by definition of pointwise multiplication, that's what x of n plus y of n. I mean, if I write it like that, you can recognize immediately, hey, that's pointwise addition of functions, right? But when we write the notation, we write it like this, right? X plus y, the nth term is x sub n plus y sub n. So it's just a different notation that we usually use for sequences. And then even is still different notation up here. These, the list notation, if you will. All right, so then next up, there is something a little bit sneakier, is what's called the LP space, LP spaces. What's an LP space? We'll end class when I finally prove something. How about that? It may be a while. So this is example 1.2.6. Here we have LP for P. What does this mean? It's the space of all infinite sequences of complex numbers, right? So I'll put it LP equals. All right, so let's say Z in this functions from the natural numbers to the complex numbers, right? Such that what? What's the condition? What does it take to be an LP? Such that the sum n equals 1 to infinity of the absolute value, which I really should say modulus here, Cn to the pth power is less than infinity. I believe these are sometimes called the p-summable sequences. So what's that actually look like? I mean, what do I mean by here Zn, you can write as xn plus Iyn, right? If you want to break it down in terms of its real notation. So like here, when I write that, what I mean is, the square root of xn squared plus yn squared. You had complex. Yay! Hey, you guys have both had complex. Woohoo! So this, of course, is the square root of zz bar. Yeah? Or did you use stars? It's either stars or bars. But yeah, depending whether you're looking at your physics books or your math book, right? I think that's where my residual uncertainty about the notation comes from as well. But so yes, so we're saying that the sequence is such that the sum of the pth powers of the moduli is finite. These are p-summable sequences. Now, it's not at all obvious. Not at all obvious why that is a subspace, right? Why is this a subspace of the function space? right? Why? Yeah.
Sorry, is the subgroup notation what we usually use for subspace notation?
Yeah, I use that for subspace notation in linear algebra.
Okay, yeah, sorry.
Uh-huh. Yeah. No, because I mean, in the sense that it's a subgroup, it's an additive subgroup. Yeah. Uh-huh. And that's I think that notation is broadly used. We won't see like the there's no need to talk about like normal subgroup in linear algebra, right? Because well, it's an abelian group, right? So every subspace is normal in that sense. You can always divide by any subspace and form the factor space in linear algebra, the quotient space. You give me a subspace, I can calculate the quotient space. In contrast, in like group theory, we can only calculate quotient spaces if our subgroup's normal. But in the context of linear algebra, the group structure here is that of an abelian group, so all subspaces are normal subgroups. But anyway, we'll eventually get back into that. Maybe. I don't know if that matters for here. But why is it that if you add two of these together, right? So if you like suppose that you have, two of these guys. Let's use x and y, right? So like suppose you have x and y in LP. So what does that give you? That gives you that the sum n equals 1 to infinity of the pth power of x modulus is less than infinity, and what else? Same for y, right? But what do we need if we're going to apply the subspace test? We need that. I guess the constant might be okay. I think the constant here is just kind of like a calculus 2 result.
He just states it.
Yeah. I mean, it wouldn't be a bad thing to like try to prove these, like the basic series. In your calculus 2, did you prove that the sum of convergent series is convergent? Well, not that. I mean, did you prove like if the sum of a sub n, is equal to L, and C is an element of, let's say, the reals for the sake of this discussion, then yeah. Yeah, did you prove that?
I don't think it was in my analysis textbook. I don't think it was proven in Calc 2, but of course we used it all the time.
Ooh, I think I forgot to move the camera. My bad. Sorry, Audric.
Sorry.
No, it's we'll reposition the room next time. We'll figure something out here. Part of it's, Audric, I just lack an extension cord. I can move the the laptop more places once I get my extension cord. So, oh man. All right, so it's not at all obvious why. Let's see here. But yeah, so this, to prove that, you just look at, like, this gives you the convergence of partial sums, and then because the when you multiply the partial sums, like the partial sums for C, the series times C is C times the partial sum of the original series, and then because the limit of the original partial sum converges, C times something which converges likewise converges. So it ultimately rests on the corresponding linearity properties of sequential limits. So yeah, I think what I'm trying to say is, like, the scalar multiple thing, I think it makes sense, right? Because if you have the sum, I'll just write it down though, for the sake of making sure we're on the same page. So if we got C times xn, right, to the p, then the thing is that that's equal to, by properties of complex, arithmetic, the absolute value, or the modulus of C rather, to the p power times this, right? And then because this is a constant, it has nothing to do with the series, you can pull it out. let's just say by calculus 2, even though we didn't prove it in calculus 2, so there's a gap. And so since that's a number and this is less than infinity, it follows that this is less than infinity, right? So therefore, C x is an element of the LP space, right? It's the addition which is more fussy. And so the textbook tells us that there's something called Minkowski's inequality. And here's what Minkowski's inequality says. Minkowski's inequality says that the sum n equals 1 to infinity of the, I'm just going to call it absolute value of xn plus yn to the p power. I used to make fun of people who did that. Now I'm doing it. Man, the 1 over p is less than or equal to the pth root of the sum n equals 1 to infinity of the absolute value of xn to the p to the 1 over to the pth root plus the pth root of the likewise series for a y. So this is called Minkowski's inequality. Now he proves the Minkowski inequality and Holder's inequality, which he proves Minkowski's inequality from Holder's inequality. All right. And that's on pages 6 and 7 of the textbook, which I'm going to skip for the moment. All right. But you see that if we know that, right, if we know this Minkowski inequality, then we're good, right? Do you see why that is? That makes sense? Well, because we're trying to show that this is less than infinity, right? And if this is bounded by the sum of that and that, well, this is less than infinity, that's less than infinity, so it's the finite. So it follows then that this is also bounded in that sense. And so therefore we have Cx and x plus y are both elements of Yp, which then by the subspace test of linear algebra, we get that LP is a subspace of the set of all complex valued sequences. But it's a particularly interesting subspace because it has to do with convergence of series, right? Yeah. So then he talks about Cartesian products of vector spaces. You guys know how to do that? Oh yeah, so sure, like yeah, sure, like so x1 Cartesian product x2 would be like x1 x2 such that x1 is an x and x2 is an x1, x2 is an x1, right? x2 rather. But he does take it to another level because he also talks about the Cartesian product with respect to a set. So like you can also, well, for one thing, you could talk about like infinite Cartesian product. So say I equals 1 to infinity, something like that, of x sub I. He gives a formal definition for that. That would be things like, you know, x1, x2, dot, 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 such that x sub I is an element of x sub I. Now he gives a more careful definition, I think. Yeah, here's his. I'm out of space. I guess I'm going back over here. So he defines like E as the product over, say, J in the index set big J. of E sub j, it's equal to the set of functions from j to the union over j and j of E sub j. So the point here is that you can take the Cartesian product with respect to an index set, and that index set doesn't have to be finite. Like here, what makes this interesting is, oh man, I keep. It's okay.
That's the function x, j into union of ej.
Right. Oh, and there's more, such that x of j is an element of ej, I think. That's part of it.
And what does it say about when you interrupt? Such that what?
What does it say where?
Where do you just wrote the first one? Yeah.
X is a function. X is a function such that x of j is an element of ej for all j. So like, this is weird in as much as you do something like j could be the real numbers, right? And so you then you're kind of, the usual notation for Cartesian product starts to fail you, right? You start having to do things like, well, x is equal to x of alpha, where alpha is a real parameter. That's the kind of notation you'd use, something like that. See, because you can't, if it's a real, there's too many to list. Now, I'm just trying to, so just to let you guys know what I'm doing at the moment, I'm just trying to wrap up section 1.2 and then we'll stop for today because, I'm going to get the call pretty soon here. So, so the last two, so we're talking about vector space. We do all these examples, right? And we're going to build on these examples next, like the next section is where it really starts to get interesting. I hate to stop here, but I'm tired. So when you're talking about vector spaces, first thing is what's a subspace? What is a vector space, right? But then shortly thereafter, you start caring about linear independence and spanning, right? So what do we mean by linear independence? Like S, a subset of E, is linearly independent if what? What does that mean? If and only if what? If and only if for any x1, x2, xk in E, we have c1x1 plus c2x2 plus plus ckxk equals to 0 implies c1 equals to c2 equals to equals to ck equals to 0. So notice here, well, okay, so that's it, right? Now, I'm not saying that this k is variable. This has to be true for all choices of k. It has to be true for 1, for k equals to 1, for k equals to 2, for k equals to 3, and so forth and so on. So I'm not sure how to exactly write that on here. I'll just tack it on at the end for all k in the natural numbers. What's spanning? So like the span, what would be the span of S? So first of all, it depends on the scalars. So if you want to emphasize that, you can write the set of scalars down here. But the span of S is simply the set of all, well, let me use summation notation if you don't mind. The sum, let's say I equals 1 to k of C sub I, x sub I, such that x sub I is an element of S. And I guess to be clear, I should probably also say K is an element of N. Now, this is a little slippery. This is a little bit different than what you saw in linear algebra. Why? What's the difference between, it's subtle, but there's just a slight difference. It's more general. It's still finite, right? Like we're looking at finite linear combinations, right? And we're still judging linear independence of the set by whether or not the trivial combination has to give you the trivial coefficients. But the difference is there could be infinitely many vectors in E. Well, there's always infinitely many vectors in a vector space over a field of characteristic 0, right? Reals or complexes are infinite, and the vector spaces over them are also infinite. But the dimension, right? So like a finite dimensional vector space, what's a basis? Remember definition? Right. Right, beta is basis for E if beta is linearly independent and the span of beta is equal to E, right? And then one of the big theorems of linear algebra, which unfortunately sometimes doesn't get proved in linear algebra, is that if your vector space is finite dimensional, then that dimension is an invariant of the space. You can't have a space which is both 8-dimensional and 10-dimensional. Dimension is a well-defined number for, if it exists, if there exists a finite basis for a vector space, all other such finite bases must have the same number of elements in it. Therefore, we can define the dimension of a finite dimensional vector space as such. Now, more generally, you can prove that any two bases for a vector space have to have the same cardinality. So, there is an extension of the notion of dimension for like infinite dimensional vector spaces where you replace numbers with cardinality. But I don't know if we need that in here. So, which is just to say, like if you have a countable basis, you're not also going to have an uncountable basis or something like that. Like if you have one basis which is as big as the natural numbers, you're not going to find another basis which is as big as the real numbers. I don't believe anyway. Now I'm treading into things I'm not sure about, but anyway, interesting questions nonetheless. So yeah, the difference here is that we have to consider arbitrary finite linear combinations here because we don't have that like benchmark of dimension n. Like when we're looking at linear independence for a finite set, the thing is if S has only finitely many things in it, if you can check it for as many things are as in it, it automatically implies lower ones. Do you see that? Like if I have 5 things in here and I have this condition for up to 5 things, it automatically implies the same condition for 4 things or for 3 things or for 2 things. Because if you suppose it's true for 5 things and not true for 2 things, well then that doesn't work, because if you have a non-trivial linear combination of 2 things which gives you 0, you can just add 3 more zeros to it and then you've violated the linear independence of the 5 things. So in the special case that S is finite, this is simpler. You don't need the for all K, you just don't be dumb about it and you do it for the things that you got there. But when you're dealing with an infinite set, you have to do it for an arbitrary finite linear combination. And, but you might be tempted to think in an infinite dimensional context, linear independence is measured by some sort of like, not this finite idea, but like a series idea. And that's not the case. Linear independence still speaks to finite linear combinations. That's how we've defined it. Yeah. Series are a lot more subtle. So, all right. So, yeah.